Good afternoon. I'm Spot On Weather meteorologist Matthew Euler, and welcome to How the Weather Works Training Series Part 7. Today we're going to take a look at the tropical areas of the Earth. We're going to look at the weather that occurs in this tropical belt. We're going to take a look at various circulation patterns within the tropics, things such as tropical easterly waves, easterly trade winds, as well as tropical cyclones. So it's a very active area of the Earth. In this particular image, showing a view from space above a very intense tropical cyclone. In general, you'll notice a very distinctive feature with a tropical system, and that is the clear area towards the center of it. And that is known as the eye, where the air actually sinks at the center of the storm, believe it or not, creating that clear area. Of course, the center of a tropical cyclone with the eye, the intensity of a storm can be determined by the diameter of the eye. The smaller the diameter, the more intense the tropical cyclone. So I'll get a little bit more into that in today's training, but I think this is really great timing for the tropical training, being that we're now sitting about 10 days out from the Atlantic tropical official beginning of hurricane season for the Atlantic Ocean. All right, so let's get right to it. First thing I'm going to do in today's training is define the tropics. We'll generally talk about some of the common features within the tropical latitudes. First of all, when I talk about the tropics, I'm talking about the area of Earth between 23.5 degrees north latitude. That specific latitude line is known as the Tropic of Cancer, and it extends down to 23.5 degrees south latitude, the Tropic of Capricorn. So the tropics range between those two latitude points. The furthest north point at 23.5 degrees north latitude, the Tropic of Cancer, and 23.5 degrees south latitude, the Tropic of Capricorn. The main features within the tropical areas include predominantly easterly trade winds. So if you live in that general area on the Earth, you pretty much get easterly trade winds throughout the course of the year. Those trade winds really don't change a whole lot. Tropical disturbances also form within this tropical belt. Those are known as easterly waves. Tropical easterly jet stream occurs. And then at the very northern point of this tropical latitude belt, we have the subtropical high pressure systems, which sit at about 30 degrees north and south latitude. And one other major features of the tropical wind belts is intertropical convergence zones. Sometimes you'll see it abbreviated as the letters ITCZ. And this is a very important area of convergence in the tropics, where the northeasterly trade winds from the northern hemisphere meet and converge with the southeasterly trade winds from the southern hemisphere. And tropical cyclones, of course, that's one of the major features that we're used to seeing. Hurricanes, if you're out in the western Pacific Ocean, western North Pacific Ocean, they're known as typhoons. And the Indian Ocean, it's known as a cyclone. But in general, sometimes these tropical cyclones can develop off that intertropical convergence zone. So that's why it's very important to keep an eye on the ITCZ. The movement of features within the tropics is generally from east to west, as those northeasterly and trade winds, northeasterly in the northern hemisphere, southeasterly trade winds in the southern hemisphere, tend to push those disturbances from east toward the west. This area, by the way, receives the most direct sunlight. So it's generally the hottest, on average, the hottest area on Earth as far as average temperatures go, compared to any other area on Earth's surface. Now, the sun is always high above the horizon between those latitudes, Tropic of Cancer at 23.5 degrees north and the Tropic of Capricorn, 23.5 degrees south. Very intense solar radiation. In fact, I at one point in time had lived in Hawaii, and my location was I was basically generally at about 21.5 degrees north latitude. And there was, I can remember, a specific time of the year in May in which the sun was directly above the horizon, most perpendicular above the horizon at 90 degrees overhead. And this in Hawaii is known as the Lahaina sun, where the sun is directly overhead at 90 degrees at a perpendicular angle to the Earth's surface. Locations within the tropics. Now, what is so unique about locations within the tropics? Well, they have very low daily temperature ranges. During the morning, the low temperature may be 78 degrees Fahrenheit or 77 degrees Fahrenheit, somewhere in there. And the afternoon high temperature may only get up to like 86 degrees Fahrenheit. So you may only have, a 5, I would even say as much as a 10 degree Fahrenheit difference between the morning low temperature and the afternoon high temperature in the tropical areas. I have made stops. I have visited Guam before, and it's very, very humid there. I can remember just walking around Guam and just dripping sweat because the humidity is always so high. That's another thing that keeps those daily temperature ranges so small between morning and afternoon, is you got a lot of humidity, especially in the western portions of the ocean basins, Western Pacific and the Western Atlantic, during the hottest times of the year in the summer. It is very, very muggy. So that excess humidity in the atmosphere tends to keep the daily temperature range fairly small between morning and afternoon. Throughout the course of the year, in addition to daily ranges being small, the yearly average annual temperature ranges are also very small. So again, I'm referring to Guam. I remember being in Guam for a few days where the morning low temperature was about 78, 79 degrees Fahrenheit, and the afternoon high temperature was 86. So it was about a 7 to 8 degree spread between the morning and the afternoon. Very intense, very warm, very, very muggy. In fact, Guam is one of those locations that has the greatest threat from those typhoons in the Western Pacific Ocean, believe it or not. Here is a look at the map here at the bottom, by the way. Let me go ahead and get my drawing tool out. Right here. Oops, wrong way here. Let me find my tool here. There it is. Okay. So I want to just point out that here is the general map of the tropical areas. Again, it extends from 23.5 degrees north latitude, the Tropic of Cancer, down to the Tropic of Capricorn at 23.5 degrees south latitude. So this is the general belt we're looking at. And you can see the different land masses that fall within the tropics. You have parts of Australia that are within that zone in the southern hemisphere. You have parts of Papua New Guinea. We go up towards the Philippines in the Western Pacific. Cambodia, Laos, Vietnam is in the tropical belt. India is in the tropical belt. Sri Lanka, as well as portions of Saudi Arabia. A large chunk of the African continent falls within the tropics. There's also a large chunk of South America that falls within this latitude belt, extending northward to Mexico. Cuba, Puerto Rico is in this belt as well. So this is generally an area that is intensely heated throughout the course of the year. The sun is always traveling throughout the course of the year between the Tropic of Cancer at the summer solstice in late June to the Tropic of Capricorn at the winter solstice in the northern hemisphere on December 21st. So the range of the sun's path throughout the course of a year is from this point down to this point. Looking at the average weather for tropical locations, I wanted to again show you graphically now, if we look at two locations, Guam and also Honolulu in Hawaii, how the ranges throughout the course of the year of these temperatures change. Now the blue line represents the average low temperatures, and the red line represents the average high temperatures. Now you see the months are located here on the horizontal axis, starting with January, going all the way to December, the end of the year. And on the vertical axis, I have the temperature in degrees Celsius. So let's start with Guam. Now, let's look at the location. Guam is generally going to be located further out in the Western Pacific Ocean basin. I don't think I've got, so I'll just point it out here on my my condensed map here showing the tropical areas. Guam is generally going to be located out in the Western Pacific in this general area here, okay, where my red little circular object is. So they're in the western Pacific Ocean. They are on the very muggy side of the Pacific high pressure system, and with much warmer water temperatures as well. And so you can look at the overall average temperatures per month and notice between the coldest month at about 29 degrees Celsius in January, it goes up to about 31 degrees Celsius in May, June time period. And then it kind of comes down very little to about 31 Celsius, eventually dropping to 30 Celsius by December. So the average annual high temperature ranges from 29 to 31 Celsius. That's it. But it's a very muggy temperature, or the humidity is very muggy and the temperatures remain consistently warm. So just to give you a reference, 30 degrees Celsius is 86 degrees Fahrenheit. Now the morning temperatures only range from about 24 degrees Celsius to about, that's about 25 degrees Celsius. So there's only a 1 degree Celsius change in the average morning temperatures each month throughout the course of the year in Guam. So a very warm and muggy location, very little. And also one thing about the climograph here I'm showing you with the temperatures is how flat these lines are, these temperature lines are. The low temperature line on the bottom, high temperature line on the top. That indicates very little change throughout the course of the year. Pretty stable. Now look at Honolulu on the other hand. Let's go back to the map. Honolulu is going to be located further toward the east. And it's generally going to be, it's located east of Guam. In general, they get northeasterly trade winds quite frequently. The Eastern Pacific high pressure system is usually located to the northeast of the Hawaiian Islands, so you get clockwise flow around the high and more of a northeast easterly trade wind regime throughout the course of the year. The water temperatures are very warm, don't get me wrong, around Hawaii, but they're kind of like, they're not as humid as a location in the western Pacific Ocean such as Guam. But let's look at the temperature changes here throughout the course of the year in Honolulu, ranging in January from an average high temperature of about 26 degrees Celsius. 26 degrees Celsius is close to 80 degrees Fahrenheit. And the warmest months are July, August, and into September in Honolulu, where the average high temperatures are just above 30 Celsius, up to 31 Celsius, and then back down again. So a range for high temperatures throughout the course of the year at a location such as Honolulu from about 26 Celsius up to about 31 Celsius. So just a slightly larger spread between the coolest and the warmest months in Honolulu as compared to Guam. And the average low temperatures range from about 19 Celsius up to about 22 Celsius. So it's about a 3-degree spread throughout the course of the year. But again, it's a tropical location. It's in that tropical belt, that latitude belt. And notice how flat, horizontal these lines are. There's not a lot of variability in the temperatures in the tropical areas. All right, so now let's get into a discussion on some of the main tropical features that we see. The first thing we're going to talk about is that ITCZ, the Intertropical Convergence Zone. This is a region of the Earth where you see surface convergence coming together from the northeast and the southeast trade winds, where they meet from both hemispheres. This area is characterized by showers and thunderstorms, and on satellite imagery, you can actually identify this feature quite readily. If I'm looking at the satellite image here in the bottom right portion of the slide, see these this line of brighter clouds here, brighter white clouds here? This is the Intertropical Convergence Zone in the Pacific Ocean. The ITCZ is located right where I'm running this red dot along. Okay. Sometimes you get disturbances to spin off this ITCZ, as I mentioned earlier, and those disturbances can move northward in the northern hemisphere and actually develop into tropical systems, tropical cyclones. The ITCZ does follow the sun's path. It enters the northern hemisphere in the northern hemisphere's summer season, and it reaches its northernmost point at that time of year. The ITCZ tends to move further south during the winter in the northern hemisphere. So it generally tends to follow the sun. And what I mean by following the sun is, as I mentioned earlier, the sun the sun's most direct rays are located at 23.5 degrees north latitude, the Tropic of Cancer. They're at the summer solstice around June 21st. During the equinox, the first day of spring, the vernal equinox, and the autumnal equinox, the first day of fall, the sun's most perpendicular rays are over the equator. And during the winter solstice in late December for the northern hemisphere, the sun's most direct rays are located over the Tropic of Capricorn at 23.5 degrees south latitude. So when I say that ITCZ follows the sun's annual journey between the Tropic of Cancer and the Tropic of Capricorn, it's very true. So in the northern hemisphere summer, when the sun is furthest north here at 23.5 degrees north latitude, the ITCZ tends to move generally north of the equator. Okay. In the northern hemisphere winter, the ITCZ is a little bit further south of the equator. So it just fluctuates based on that sun's journey. I just wanted to point that out. Now the ITCZ is important in that it provides the lift mechanism that's necessary to create these cumulus clouds and these tall thunderstorm cumulonimbus clouds and heavy showery precipitation. In fact, some areas of the world rely exclusively on the ITCZ at certain times of the year for giving their location the rain they need. Sensible heat from solar radiation and heating from warm tropical waters tends to provide a warm source region. And what this does is it distributes latent heat aloft and creates these large hot towers of convection. There's one thing for sure that I noticed when I've been in the tropical areas of the world. I have noticed those puffy towering cumulus clouds. And that is a visible sign that is basically indicating to me that there is vertical heat being redistributed from the surface higher up to the cooler portions of the atmosphere. I saw quite a few towering cumulus and cumulonimbus clouds, especially in a location such as Guam, because of their location within the tropics. Now, I didn't necessarily put subtropical highs. I wouldn't necessarily include it within that 23.5 degrees north latitude to 23.5 degrees south latitude, that particular latitude belt. But it's very important in the overall tropical circulation, and that's why I'm throwing it in today's training. This subtropical high, anytime in the atmosphere we talk about pressure systems, air tends to always blow from high towards lower pressure. We look at the graphic here on the bottom right. You'll notice these blue H's. These are those subtropical high pressure systems, which are very important. They're situated at 30 degrees north and south latitude. And we have one particular subtropical high known as the Eastern Pacific High located in the Eastern Pacific. There's another subtropical high located over the Atlantic, and that's known as the Azores or Bermuda High. And the circulations around these high pressure systems are very important as far as steering tropical cyclones on their western peripheries, as well as the flow around these high pressure systems is clockwise in the northern hemisphere, for example. And you'll notice the white arrow showing the wind direction, okay, how the air is moving in the atmosphere. This red dashed line is a belt of low pressure known as the ITCZ, the Intertropical Convergence Zone, this red dash line. And this is an area of low pressure in the atmosphere. So air is always going to blow from the subtropical high pressure towards the Intertropical Convergence Zone. And so what you have, as the wind blows clockwise around the high, moving from the north to south on the eastern side of the subtropical highs in the northern hemisphere, the wind is turned slightly to the right of its intended path of direction, and that's due to the Coriolis force. So subtropical highs are very important as far as establishment of a predominant easterly trade wind across tropical areas on Earth, whether we're talking northern hemisphere with the northeast trade winds or the southern hemisphere with these southeast trade winds. And they are a very critical portion of heat balancing in the atmosphere on the Earth as a whole. Additionally, Again, as I mentioned, subtropical highs tend to steer tropical cyclones from lower latitudes towards the middle latitudes. And so you'll notice that the Hurricane Center, when you have an active tropical cyclone actually moving, let's just use the Atlantic Ocean, the Western Atlantic Ocean as an example, they'll always be talking about the orientation of this ridge or the subtropical high. Where this high is located is very key. How intense the tropical cyclone is also very key as far as steering winds. But in general, this high pressure system has a lot to do with where tropical cyclones end up, whether they make landfall into the east coast of the United States, whether they stay south and go into Central America, whether these tropical cyclones recurve into the Gulf of Mexico and impact the Gulf states or Florida. The subtropical highs are a very important part of tropical weather. All right, so now speaking of tropical weather, let's move into a discussion on tropical cyclone formation requirements. What are the necessary ingredients to cause these systems to develop? The first one is we need a warm sea surface temperature. It needs to be greater than 79 degrees Fahrenheit. This very warm water acts as a fuel source of both heat and moisture for tropical cyclones. Coriolis force must be vigorous enough to promote rotation, some kind of rotation as a tropical disturbance gets developed. We need some kind of twisting motion to the air, and that can occur only, you got to be at least 5 degrees latitude away from the equator, either north or south, to get that. If you're within 5 degrees latitude of the equator, the Coriolis force is generally too weak, so you're not going to get that twisting motion you need to really get a tropical cyclone going. Additionally, we look at something known as convective instability of the second kind. It's abbreviated CISK. Now, it's kind of funny because it kind of reminds me of the old movie Close Encounters of the Third Kind, when you had the alien ship come down to Earth. When I see the second kind, it kind of makes me chuckle a little bit. But what this means, CISK, convective instability of the second kind, it basically represents the area of divergence aloft. You need that exhaust above a tropical cyclone to remove the mass aloft and to increase the low-level convergence over the warm ocean waters. Additionally, light vertical wind shear. You're looking for light vertical wind shear. You want most of the energy with a tropical cyclone to really intensify. You want most of the energy to be directed straight in the vertical. If you get any kind of wind shear, what it tends to do is it tends to tilt your updrafts in developing hot convective towers. It tends to cause those updrafts to become more slanted at an angle, and so your energy is not as concentrated when you have a slanted updraft versus a straight up and down vertical updraft. So you need good outflow or divergence aloft with convective instability of the second kind. You have the moisture source and the heat source from the warm tropical waters have to be 79 degrees Fahrenheit or warmer. And you need to be at 5 degrees, at least 5 degrees latitude, north or south from the equator. All right, with tropical cyclone development process, let's move into that. So we talked about formation requirements, and now let's talk about development process. An easterly jet stream tends to exist in the tropical latitude belt. This generally forms at about 15 degrees latitude in the northern hemisphere. I'll just use the northern hemisphere as an example. The exit regions of these jet streaks, so just like we have with the mid-latitude jet stream, the polar front jet stream, where we have these accelerated regions of wind velocity, we also have a similar situation in the tropical jet streaks, or the easterly jet stream, where we have these jet streaks or accelerated regions of fast-moving air embedded in these easterly jets. That tends to promote divergence aloft and that low-level convergence at the surface. And what that then tends to do is produce what's known as a thermal trough at the surface, which tends to intensify, with easterly outflow aloft producing easterly waves. Those are the disturbances within the tropical wind belt that move from the east toward the west. They're called easterly waves. There's two general types of easterly waves. I won't really get too deep into the weeds on that, but there's a stable easterly wave as well as an unstable easterly wave. Now, easterly waves are generally going to be inverted troughs moving from the east to the west, and they can supply the upper level divergence required to make that convective instability of the second kind work. They tend to sustain convective cells where you get rising vertical air motion, stronger updrafts, and support creation of low pressure at the surface. So let me do a quick drawing for you. Let me go right back here. Okay. So in general, in the mid-latitudes, when we talk about mid-latitude troughs, their orientation is generally going to be like this. It's going to look like a U-shaped pattern. That's a mid-latitude trough. So your trough axis is going to generally extend from the north towards the south in the mid-latitudes. In the tropical areas with these easterly waves, you get what's known as an inverted trough, where it's an upside-down U-shape pattern, and you get these easterly waves. This is easterly wave. This is the troughs within these easterly waves within the tropical latitude belt. So you have an inverted trough. That's an upside-down shaped U. That's what we mean when we say inverted troughs. And generally, these little easterly waves tend to move from the east towards the west, being steered by the easterly trade winds. Okay? Now, as I mentioned, there's two types of easterly waves. There's stable easterly waves and unstable easterly waves. But in general, what you have is you have areas of upper level divergence that get going aloft above these easterly waves, and that tends to lead to some increased low-level convergence where the air comes together and rises in the vertical. And if the divergence is very strong, it will tend to increase the convergence at the low levels. And what you get is a self-sustaining heat engine, so to speak. You get these continuous convective towering cumulus clouds. You get this heat energy being injected into the system, rising in the vertical, and then eventually you get the creation of low pressure at the surface. I just wanted to show you the difference between a mid-latitude trough, okay, that's more of this U-shaped pattern to the height contours. And here your trough axis, the mid-latitude generally extends from north to south. Whereas in the tropical wind belt, you generally get these inverted troughs, which are an upside-down U shape, and they generally tend to extend from south to the north. Okay? So in the absence of the synoptic scale wind shear again is just simply a change in wind direction and speed with height. When you get a lot of wind shear, it tends to disrupt or tear apart thunderstorms. And so it does not allow those thunderstorms to really develop. It tends to tear apart thunderstorm tops. And tropical systems have a very difficult time surviving when you get a lot of wind shear. If you get mid-latitude systems that are very strong and dynamic in nature, and they extend further to the south into the tropical areas, like, for example, in the fall, especially in October, November time period, you get these very strong mid-latitude systems, very deep mid-latitude troughs that extend into the tropical areas. That tends to increase the wind shear, which is not what you want for a tropical cyclone to develop. It'll actually weaken or inhibit development. But generally, a positive feedback loop occurs within a tropical cyclone, and it can self-perpetuate the cyclostrophic wind flow, allowing for tropical cyclones to intensify. Now, that word cyclostrophic, okay, I'm going to go right back here. That word cyclostrophic, this word right here, that is basically a wind that tends to occur with very intense low pressure systems, with very small curvatures, radius of curvature. And so an example of a cyclostrophic wind in the atmosphere would be a tornadic wind around a funnel cloud. You have very extremely low pressure over a very short distance. It tends to lead to extremely devastating winds. The same goes with tropical cyclones. And I kind of hinted at that with the size of the eye, the diameter of the eye. The smaller the diameter, the stronger the winds are going to blow, the more devastating the storm is going to be, the more intense it's going to be when you have stronger cyclostrophic flow rotating around the eye, around the center of circulation. So hopefully that helped explain what cyclostrophic means. Very low barometric pressure, very short distances. Two examples in the atmosphere would be a tornado and also tropical cyclones. Now, the conservation of angular momentum comes into play as a cyclostrophic wind flow tightens around, intensifying the low pressure areas. There it is, the definition of cyclostrophic flow. I also put it here for you to read and see just that wind characterized by extremely low barometric pressure, very tight curvature radius, very strong wind speeds. I mentioned it also occurs in tornadoes. Okay, so there's a couple things going on here. When we talk about a very tight curvature radius, whether we're talking a tornado or a tropical cyclone, this conservation of angular momentum comes into play, trying to counteract that cyclostrophic wind flow. One thing you may not know is radiative cooling occurs from tall thunderstorm tops, very high up in the atmosphere. These could be at 65 to 70,000 feet above the ground. Especially at nighttime in the tropics, you get this radiative cooling, this cooling from tall thunderstorm tops. That can enhance the instability further because you're lowering the environmental air temperature. Creates colder layers aloft and increases the environmental lapse rate, makes it more steep or unstable. This allows warm air parcels to continue to rise even higher. This process will then allow developing tropical disturbances to grow by creating more vigorous thunderstorms. And once formed, the upper level divergence must continue, and what usually happens is you get this upper level anticyclonic outflow aloft. You get an area of high pressure in the upper levels of the atmosphere to exist over a tropical cyclone. And that serves to remove all the mass aloft. It provides an exhaust system for this heat engine known as a tropical cyclone. Several events can disrupt or prevent formation of tropical cyclones. The first one, which I've already kind of talked about, is the upper level wind shear. Wind shear is a change in wind velocity, wind speed, and direction with height. What that tends to do is it alters the closed circulation of the cyclone. It slants that vertical convection. This disrupts the chimney effect greatly and tears the storm apart. If a tropical cyclone falls under the influence of those nearby synoptic scale low pressure systems, I talked about, especially in the fall in October and November, where you get the polar front jet stream starts moving further south and you get stronger extratropical or mid-latitude cyclones to dip further into the tropics. If you get these kind of influences with the jet stream tending to increase the wind shear, it can rob the storm, a tropical cyclone, of some of its convective fuel, since it's competing in a competing region of surface convergence. There's actually something, and I don't have it in today's training, but there's something that is known as the Fujiwara effect. And this occurs when you get two tropical cyclones close in proximity to each other in the tropics. And what happens is there's competition for the energy in the atmosphere. If these two tropical cyclones get too close to each other, one of the systems is going to rob the energy from the other one. So usually it's a case of comparing the intensities of the cyclones. If you have a weaker tropical cyclone next to a very strong tropical cyclone, the tropical cyclone will usually take the energy from the weaker tropical cyclone, and that weaker tropical cyclone tends to weaken significantly. And so there's something known as a Fujiwara effect. In addition, we talk about Fujiwara effect. We also talk about how the overall circulation of the two cyclones can actually, the two cyclones spinning at the same time can cause a circulation where they spin around each other. Pretty neat stuff. Here is the vertical structure of a tropical cyclone. Hurricanes are generally warm core barotropic systems with anticyclone aloft, high pressure aloft. Some of this, here you see the blue H, this is your high pressure aloft. Okay. Some of the anticyclonic flow aloft is generally going to re-enter the eye of the storm, subsiding there, so you have sinking air motion at the eye because of this high pressure aloft. And the air, as it sinks, it compresses, it dries out, and it results in a relatively clear area at the center of the tropical cyclone. So you get generally warm, calm, and often cloudless weather in the eye. So if you're on the Earth's surface at this location beneath the eye, people have been fooled before in the past where they have one side of the hurricane hit and then the eye comes overhead and they think the storm's completely over. Unfortunately, that's not the case, because then the other side of the eye comes in and the weather goes downhill relatively quickly again. Cyclonic circulation exists down at the surface. You have a surface low pressure system. Again, it's a warm core barotropic low. You have these red arrows represent the converging air over this very warm and moist ocean surface. This water is the fuel to really intensify and keep this storm. It keeps feeding the storm the energy it needs to survive and self-sustain. And so low-level convergence at the surface, area of low pressure, and then you get the rising air motion in these eye walls. These eye walls have the most intense weather associated with tropical cyclones. Eye walls have the strongest winds. Eye walls tend to have just the nastiest weather. You generally get very heavy rain showers, damaging winds, as I mentioned already. You can actually get tornadoes to spin off, quick spin up to tornadoes. When we're talking about the northeastern side of the storm, the northeastern eye wall. In addition, with eye walls, there's something known as the eye wall replacement cycle. And what happens is, the very intense tropical cyclones, you get one primary eye wall, okay? And as another eye wall tries to develop, a more outward directed eye wall tries to develop around an inner eye wall, the outer eye wall tends to contract and move closer to the center of the storm itself, and it temporarily weakens the storm when this happens until that eye wall replacement cycle is complete, in which the outer eye wall absorbs the energy from the inner eye wall. And you can get some really very, very intense hurricanes to make landfall up at category 5 level. With the eye wall replacement cycle, the timing of that is so very critical. Additionally, in addition to the eye wall, you notice how this air just moves outward or diverges aloft away from the eye walls. Then it tends to sink on the outer edge of the hurricane, and generally it moves back in towards the center again. Now you do have some up and down motion, vertical motion, associated with these rain bands as well, where you get quick hitting showers and gusty winds. The showers tend to start and stop rather quickly, and then you may be quiet and not have anything. You may see blue sky actually in between these rain bands, and then you get hit with another rain band, and it gets progressively worse. The winds, as well as the precip, it tends to get progressively worse the closer you get to this eye wall and the eye of the hurricane itself. So you have cyclonic circulation at the surface, spiraling bands of cumulus clouds that produces the high winds and heavy showers associated with these rain bands. And depending on their vertical extent, tropical cyclones are generally steered by the motion of mid and upper level winds. And once the storm is over land, generally these tropical cyclones are going to weaken drastically due to the lack of their heat energy source, the moisture, as well as the force of friction induced by the land. This results in an expansion or widening of the energy and overall weakening trend of tropical cyclones. Here are some of the favorable tropical cyclone areas across the world. The orange shading indicates areas in which tropical storms typically form. So there's a lot of areas that are impacted across the world by these tropical systems. Of course, we're very familiar with it. If we live in the United States, if you live in the U.S., there is, across the tropical Atlantic, systems can form, the Caribbean, as well as Gulf of Mexico. Bay of Campeche is another favorable area at certain times of the year. Eastern Pacific has its share of hurricanes and tropical systems that develop. These white arrows generally tend to represent the tracks of the systems, by the way. And then Indian Ocean, the tropical cyclones are known just simply as cyclones. They impact places in the Indian Ocean, can also impact areas of Australia, these cyclones, as well as India. Additionally, in the Western Pacific Ocean, you generally have typhoons. It's the same type of storm as a hurricane, it's just a different name, a different naming convention for storms that form west of 180 degrees west longitude in the Western Pacific. They're known as typhoons. And here are some of the points of curvature, how they generally tend to move. One thing I wanted to mention to you again is the importance of that high pressure system. In general, we have this tropical high located out at 30 degrees latitude in the Atlantic Ocean, 30 degrees north latitude, and the clockwise flow around these highs generally tends to steer tropical systems. The same thing goes out in the Pacific Ocean, where if you have higher pressure up here to the north, it generally tends to steer the clockwise flow around highs. Generally tends to steer these tropical systems towards the west-northwest in the northern hemisphere. Right, so just wanted to kind of show you the general climatology of where these tropical the favorable areas for tropical cyclones. And then here is the actual track and intensity overlay of all tropical storms. And you can tell the color scheme here how intense the systems are. So if I have the orange shading, if I have this orange shading over the western Pacific Ocean, the darker orange shading, that's associated with Category 5 or very strong typhoons in that location. You also see a lot of tracks over the Gulf of Mexico, the Caribbean, the western Atlantic Ocean. You see a lot of orange coloring, and they're also more intense in these areas. In the southern hemisphere, you see a lot of tracks down there as well, to the northeast of Australia. Northern Australia is the one that mainly gets impacted by tropical cyclones, and then out over the Indian Ocean as well. And there's been some doozy cyclones into India as well. Cannot neglect to mention that for sure. They've had some catastrophic flooding associated with some of these tropical cyclones that move into India. Now, what about certain phenomenon and their impact on tropical seasons? Tropical activity in general. You'll notice every year when the National Hurricane Center issues its outlook, one of the major factors they look at is whether there's an El Nino or a La Nina. Okay? During El Ninos, here's a nice graphic to kind of break it down. During El Ninos, what you have is increased wind shear across the Gulf of Mexico and the western Atlantic Ocean in this area here. During El Ninos. So increased wind shear, remember, is not favorable for tropical cyclones to develop at all. So you generally tend to get fewer hurricanes due to stronger vertical wind shear and stronger than normal trade winds. Greater atmospheric stability during El Nino years out in the Atlantic Ocean side. But in the eastern Pacific side during El Ninos, you tend to get more hurricanes. There tends to be less vertical wind shear in the eastern Pacific during the El Nino years. So, this is my summary of El Nino impacts on tropical cyclones, fewer hurricanes in the Atlantic Ocean basin due to the increased vertical wind shear, stronger upper level winds that tend to rip apart any type of thunderstorms that try to develop with any of these tropical disturbances or easterly waves. Tend to get more hurricanes in the eastern Pacific Ocean basin due to decreased vertical wind shear. So, El Nino definitely impacts places such as Hawaii. They tend to get there's a greater risk of a hurricane impacting the Hawaiian Islands during El Nino seasons. La Nina, on the other hand, which we currently we're currently in La Nina, we tend to see more storms now across the Atlantic Ocean basin. And that's due to decreased wind shear in this particular area of the world. And you tend to get fewer storms due to increased wind shear in the eastern Pacific. So the roles have basically flipped, right? With La Nina, you tend to get more active hurricane seasons in the Atlantic Ocean basin and less active hurricane seasons in the eastern Pacific Ocean basin. So real interesting. I just wanted to tie the impacts of teleconnections on the overall tropical cyclone seasons as well in today's training, just to kind of show you that. Now this year we are definitely in La Nina. I would not be surprised if the official outlook from NOAA shows an expected above average season for the Atlantic Ocean, for the Atlantic Basin. I would not be surprised because we're now entering the third year of La Nina conditions where the water off the eastern and central equatorial Pacific is cooler than normal. Okay, that tends to have decreased upper level winds in the Atlantic side, which tends to favor more tropical cyclone development. So the outlook should be coming out fairly shortly from from NOAA, from the Hurricane Center, I have seen some of the outlooks already issued by Colorado State University calling for an above average season in the Atlantic Ocean basin this year for hurricanes. And again, one of the primary factors in that forecast is the La Nina. Okay, that wraps up the train today. We talked about quite a few things here, and I really hope you enjoyed the training. We started off with just defining the tropics in general. The location of Earth between 23.5 degrees north latitude, the Tropic of Cancer, to 23.5 degrees south latitude, the Tropic of Capricorn. Some of the major features within the tropical wind belts include predominantly easterly trade winds. Winds generally blow from the east year-round. Tropical disturbances known as easterly waves. Tropical easterly jets. Subtropical high-pressure systems. Intertropical convergence zone, where you get an area of thunderstorm activity as the trade winds converge from both hemispheres. And then, of course, what we're most familiar with are tropical cyclones. Hurricanes and typhoons definitely get our attention because they're such strong storms and can inflict great damage to coastal areas. The movement of the features, generally in the tropics, is from east to west as those easterly trade winds push along the disturbances. Don't forget, this area of Earth receives the most direct sunlight. The sun is overhead throughout the course of the year as the sun makes its annual journey between the Tropic of Cancer and Tropic of Capricorn. Very intense incoming solar radiation reaching the surface. Just showed how an area, some of the cities within the tropics generally have lower diurnal or daily temperature ranges, as well as very small annual temperature changes throughout the course of the year. Here were a couple locations I gave in today's training, Guam versus Honolulu. Again, one of the most important things to look at is the shape of these lines. Look how horizontal or flat these lines are in both cases. There's not a lot of variability is what that means in the temperature throughout the course of the year from January to December. We also talked about one of the major features in the tropics, and that would be the intertropical convergence zone. And you can identify that in satellite imagery. Just pull up a satellite image and you can definitely identify where it's located. It's more of a continuous line of showers and thunderstorms that you'll notice. The ITCZ tends to follow the sun's path. It enters the northern hemisphere in the summer season and reaches its northernmost point at that point in time throughout the year. Additionally, we talked about subtropical highs and their importance within the tropical circulation. We talked about how these subtropical highs tend to steer tropical cyclones on their western periphery, or their western side, towards the east coast of the United States, towards the Gulf of Mexico, or in the western Pacific Ocean basin. Those highs also tend to steer these storms towards Vietnam, towards the Philippines, towards Japan. Some of the tropical cyclone formation requirements, we talked about that, about having a warm water surface to act as that fuel source, greater than 79 degrees Fahrenheit. You must have the Coriolis force, or that twisting motion, north or south of 5 degrees latitude from the equator. You also have a process known as convective instability of the second kind, where you get upper level divergence aloft that exists over the surface circulation, that low pressure at the surface, that tends to act as an exhaust mechanism. You also need light vertical wind shear, so not much change in wind speed or wind direction with height. And then we talked about how the tropical cyclone development process occurs. Initially, you may have an easterly jet around 15 degrees north latitude in the northern hemisphere. You get these exit regions of the jet streaks, accelerated regions of wind velocity embedded in these jets, easterly jets, which promote divergence aloft and convergence at the surface. You get that circulation developed initially. This is going to produce an area of lower pressure at the surface, or a thermal trough. That will tend to intensify over time with easterly outflow aloft, producing these easterly waves within areas of upper level divergence. In other words, you get an area of surface low pressure to develop. You definitely don't want to have any of that wind shear. You also do not want to have any of the middle latitude systems, stronger middle latitude systems, pressure systems moving into the tropics, because that tends to rob energy away from these tropical cyclones and also increases wind shear. We talked about other things here when we talk about development process, how cloud tops tend to give off cooling, tend to cool the surrounding environment, especially at night in the tropics, which tends to enhance the instability. It creates colder environmental temperatures or layers aloft, and this is going to increase or steepen the environmental lapse rate. That's going to allow those warm air parcels to become more positively buoyant and want to rise even higher in the atmosphere. This generally results in more vigorous thunderstorms. If you look at enhanced infrared satellite imagery at night and you see a pulsing nature to tropical disturbances, that's exactly what's going on. So that's kind of something cool to think about. Eventually what happens, wind shear is weak, and you get low pressure, low level convergence increasing, upper level divergence aloft, and you get this structure of a hurricane or tropical cyclone that looks like this, where we have sinking air motion in the eye, generally associated with clear sky, very light winds in the eye. These systems overall, tropical cyclones, are warm core barotropic systems, and high pressure aloft tends to evacuate. See the red arrows here spreading apart in the upper levels of the atmosphere. That tends to provide that upper level divergence, remove the mass aloft, that increases at low level convergence at the surface, causes the air to rise more vigorously in the eye walls, the eye wall portion of the storm. Here are favorable locations of tropical cyclone development areas across the world. And in general, the importance of the subtropical high and how it will steer the clockwise flow around these highs, how it steers the systems towards the Gulf of Mexico, towards the eastern U.S., in the western Pacific, towards Philippines, towards China, towards Guam, towards Japan. And then in the southern hemisphere, how the high pressure systems, they have a counterclockwise flow, and they tend to steer the systems towards Australia, as well as Madagascar. Here is a look at the frequency and the intensity of all tropical storms, tropical systems in general. The most intense tropical cyclones are going to be located over the western Pacific Ocean, where we get super typhoons. And in the Atlantic Ocean, you can see the orange coloring here. We've had some pretty strong storms in the Atlantic as well. And then in the southern hemisphere, the general location where you see tropical activity. And then finally, today's training, I closed out with the El Nino impacts and La Nina impacts on tropical cyclones. Generally, during El Nino, you have fewer hurricanes in the Atlantic Ocean basin, more hurricanes in the eastern Pacific Ocean basin. La Nina is the opposite, where we have now more storms due to less wind shear in the Atlantic Ocean basin, and we have fewer storms in the eastern Pacific Ocean basin due to more wind shear. So that wraps up today's training on the tropics. I hope you enjoyed it greatly. This is How the Weather Works Training Series Part 7. Got a lot more training to follow. I'm looking forward to giving it and sharing this knowledge with you all. Wherever you're watching from, greatly appreciate your subscription to the Spot On Weather YouTube channel. I like to really focus in on training. Of course, I interrupt this training during the summer season if we got major hurricane activity that looks like it'll be a threat. I will occasionally make special hurricane videos for updates for everybody. Okay, until next time, until the next training session, I wish everybody the best. Hope everything's going well for everybody out there watching. And until next time, take care and God bless everyone.